Let's delve into the essence of our physical world. Matter. Matter is the substance that makes up everything around us. It exists in various forms: solids, liquids, and gases. From the air we breathe to the ground beneath our feet, matter is the fabric of our reality. From the vast cosmic reaches to the microscopic wonders of life, everything around us, from black holes to the smallest bacteria, is intricately woven together by the common thread of atoms. At the cosmic scale, we encounter black holes, enigmatic celestial entities born from the gravitational collapse of massive stars. These cosmic giants exert such immense gravitational force that even light cannot escape their grasp. Despite their mysterious nature, the matter that makes up a black hole, just like everything else, is composed of atoms. Zooming in on our solar system, we find the radiant heart of our existence: the Sun. This colossal ball of plasma is fueled by nuclear fusion at its core, where hydrogen atoms are transformed into helium, releasing an incredible amount of energy. It's this energy that sustains life on Earth, reminding us that even the powerhouse of our solar system is fundamentally made up of atoms. Shifting our focus to the microscopic realm, we encounter the humble yet crucial bacteria. These single-celled organisms, often overlooked, play vital roles in ecosystems, from aiding digestion to decomposing organic matter. Despite their size, bacteria are complex structures, composed of atoms orchestrating their functions. Now, journeying to the diverse ecosystems of land and sea, we find a breathtaking array of animals. Whether soaring through the skies, roaming the savannas, or swimming in the oceans, each creature, from the smallest to the largest, is a marvel of biological engineering. Their bodies, organs, and tissues, all formed by the intricate dance of atoms. In this grand tapestry of the universe, atoms serve as the fundamental bricks, shaping the cosmos, energizing stars, fueling life, and constructing every living being. From the vast expanse of space to the smallest corners of our planet, the unity of all things, bound by the shared language of atoms, underscores the interconnectedness of our existence. Thus, we can properly define an atom as the fundamental unit of matter, constituting the basic building block of all elements. But if everything is made up of atoms, what are atoms made up of? Comprising a nucleus at its center, an atom is characterized by positively charged protons and electrically neutral neutrons within the nucleus. Orbiting the nucleus are negatively charged electrons, which determine the atom's chemical properties and interactions. Atoms combine to form molecules, and their intricate configurations give rise to the diverse substances observed in the universe. Despite their minuscule size, atoms are essential in shaping the physical and chemical properties of everything in the cosmos. The masses of subatomic particles are typically expressed in atomic mass units, AMU. Proton mass equals 1 AMU. Neutron mass equals 1 AMU. Electron mass equals 0.00054857 AMU. It's important to note that the mass of an electron is much smaller than that of a proton or neutron, contributing significantly less to the overall mass of an atom. The arrangement of electrons orbiting the nucleus is referred to as electronic configuration. The electronic configuration dictates how an atom interacts with others, influencing its ability to form chemical bonds and engage in reactions. This understanding is crucial for explaining the properties and behaviors of elements in the periodic table. Now let's look at the number of shells of the atom, and how many electrons each shell can hold. K shell can hold maximum of 2 electrons. L shell can hold maximum of 8 electrons. M shell can hold maximum of 18 electrons. N shell can hold maximum of 32 electrons. O shell can hold maximum of 32 electrons. P shell can hold maximum of 18 electrons. Q shell can hold maximum of 8 electrons. Now let's have a look at the electronic configuration of first 10 elements of the periodic table. First up, we have hydrogen. It has only one shell and one electron. Helium also has only one shell, but it 2 electrons in that shell. Lithium has 2 electrons in the first shell, and 1 electron in the second shell. Beryllium has 2 electrons in the first shell, and 2 electrons in the second shell. Boron has 2 electrons in the first shell, and 3 electrons in the second shell. Carbon has 2 electrons in the first shell, and 4 electrons in the second shell. Nitrogen has 2 electrons in the first shell, and 5 electrons in the second shell. Oxygen has 2 electrons in the first shell, and 6 electrons in the second shell. Fluorine has 2 electrons in the first shell, and 7 electrons in the second shell. Neon has 2 electrons in the first shell, and 8 electrons in the second shell. Okay. Now that we have learnt about atoms, subatomic particles, and how atoms of first 10 elements look like, let's understand how they react and make compounds. The behavior of atoms in chemical reactions is primarily determined by the arrangement and interactions of their electrons. The electrons in the outermost shell of an atom are called valence electrons. These electrons are crucial in determining how atoms will react and form compounds. Here is a table of valency. Look at the table carefully and understand how atoms tend to gain, lose, or share electrons in order to achieve a stable electron configuration similar to that of noble gases, which typically have 8 electrons in their outer shell. This is known as the octet rule. Whenever an atom gains or loses an electron, an ion is formed. Ions are charged particles that result from the gain or loss of electrons by atoms. Ions are typically formed during chemical reactions, where atoms gain or lose electrons to achieve a more stable electron configuration. Elements in groups 1 and 2, alkali and alkaline earth metals, tend to lose electrons to form cations. Elements in groups 16 and 17, chalcogens and halogens, tend to gain electrons to form anions. There are 2 main types of ions: cations and anions. A cation is a positively charged ion. It forms when an atom loses 1 or more electrons. The loss of electrons leaves the atom with more protons than electrons, giving it a net positive charge. Common examples include metal ions like sodium ion and calcium ion. An anion is a negatively charged ion. It forms when an atom gains 1 or more electrons. The addition of electrons results in more electrons than protons, giving the ion a net negative charge. Common examples include nonmetal ions like chloride ion and oxide ion. In summary, cations are positively charged ions formed by the loss of electrons, while anions are negatively charged ions formed by the gain of electrons. The combination of cations and anions leads to the formation of ionic compounds. In ionic bonding, atoms transfer electrons to achieve a full outer shell. For example, sodium can lose 1 electron to achieve a stable configuration, becoming a positively charged ion, while chlorine can gain that electron to become a negatively charged ion. The oppositely charged ions attract each other, forming an ionic bond. This is common in compounds like sodium chloride. In another type of bonding, known as covalent bonding, atoms share electrons to achieve a full outer shell. For example, in a water molecule, each hydrogen atom shares its electron with the oxygen atom. Covalent bonds are common in molecules like methane and oxygen. The table provides a systematic way to understand the relationships between elements and predict their behavior in chemical reactions. This table isn't just a chart, it's a roadmap guiding us through the world of chemistry. At its core, the periodic table showcases periodicity, the recurring pattern of properties that stems from the arrangement of elements. Elements are organized based on their atomic number, which represents the number of protons in an atom. This arrangement gives rise to periods, the horizontal rows, and groups, the vertical columns. Now, why does this matter? Well, it's a blueprint for understanding the behavior of elements. For instance, elements in the same group share similar chemical behaviors because they have the same number of valence electrons. And when you traverse a period from left to right, you're exploring changes in properties linked to increasing atomic number. Elements tend to become less metallic and more non-metallic as you move across a period. It's a systematic guide that unlocks the secrets of each element's characteristics and behavior. In the late 19th century, where brilliant minds like Mendeleev and Moseley paved the way, the periodic law emerged, unlocking a systematic arrangement based on atomic number, leading us to the structure we know today. Now, let's dissect the table. It's organized into periods and groups. The atomic number takes the spotlight, dictating an element's position. Deciphering the table unlocks a wealth of information. Each block tells a story. It's a code revealing the secrets of the elements. The table's brilliance lies in predicting an element's characteristics based on its position. Elements in the same group often exhibit similar traits, making it a powerful tool for understanding and predicting chemical reactions. Groups and periods are the fundamental coordinates on the periodic table, revealing crucial details about an element's properties. Groups. These are the vertical columns, and there are 18 of them. They are classified as A and B. The classification stems from the electron configurations of the elements. Groups A. These include the main groups and are labeled from 1, 2, 13, 14, 15, 16, 17 and 18. Elements in these groups have predictable and straightforward electron configurations, making them easier to categorize. Groups B. These are also known as the transition metals. They consist of the transition elements, spanning groups 3 to 12. The electron configurations of these elements are more complex due to the presence of inner electron shells. Periods. These are the horizontal rows, and there are 7 of them. The period number indicates the energy level of an element's outer electrons, with higher periods having more energy levels. Formation of group and period numbers. The group number is linked to the number of valence electrons, while the period number corresponds to the principal energy level of the outer electrons. These numbers provide a systematic way to navigate the periodic table and understand the arrangement and behavior of elements. And thus we complete today's lecture. I hope you have fully understood the structure of atoms, formation of matter, and arrangement of elements in the periodic table. As always, if you have any question, leave it down in the comment section, and I will answer you as soon as I can.